Um, and once again, good morning to one and all. Uh, my name is Kiran, and I'm an associate professor of mechanical engineering in KL University, and also acting as associate in quality. And basically, I'm a mechanical engineer. I have my graduation in mechanical engineering at SB University Tirupati, and my master's from NH Varanga with a specialization in advanced manufacturing processes. I have over 10 years of professional experience in over 7 years of industrial experience as senior software engineer, project engineer, CA engineer, and a CAE analyst using various IT tools and packages like C++, Java, .NET, SAP, Oracle, and also various mechanical packages like Creo, HyperWorks, Meshworks, ANSA, Nastron, Elastina, and so on. With all my industrial experience, I registered my full-time PhD in NIT Warangal in the area designed for crashworthiness. After my PhD, I joined as an associate professor at KL Geometry University, and I completed my 3 years of post-PhD experience with KLU as an academician. During these 3 years, in addition to teaching, I was responsible for various administration loads like course coordinator for various graduation and post-graduation courses, board of studies internal member, professor in charge for faculty orientation lectures and guest lectures, machine tools, lab in charge, professor in charge for department examination cell, chief superintendent for KLDM to University examinations, and currently doing as an associate in quality. Today, I'm here in front of you as a speaker to talk on automotive design for crashworthiness using CAE methodologies. Before starting this session, I'd like to ask a few questions. How many of you are having four-wheelers? Whoever is having passenger vehicles, please raise your hands in your chins. Can I see the responses? Okay, I'm not getting any response over here. Okay, so as a normal user of four-wheeler vehicle itself, we should know the safety rating of our vehicle. But especially as a mechanical engineer, we must know that safety standards of our vehicle, which represent the safety of vehicle in terms of star rating. At the end of this session, we'll come to know what is the star rating and how it would be assigned to any passenger vehicle or any other vehicles. Crashworthiness of a vehicle can be defined as its ability to protect its passenger and other participants, like pedestrians and other vehicles involved in impact. The car body structure is one of the important vehicle systems that helps in mitigating the impact loads. Therefore, appropriate design measures should be taken while designing the car body structure. In general, design of a vehicle body structure affects the performance of vehicle in almost all aspects such as safety, comfort, and fuel consumption. Therefore, various criteria in the field of structural mechanics and aerodynamics are used while generating the design of body structure. This makes the design process highly complex, iterative, costly, and time-consuming. As an aid for this design process, computer-aided methods CAD, computer-aided design, and computer-aided engineering (CAE) are extensively used in the present automotive industry. With the help of CAD techniques, car body structure can be constructed and modified easily. The ability of the CAD systems to create parametric designs helps in increasing the productivity of the design process. Using the CAE techniques, the constructed structure can be visually analyzed and optimized for various loading scenarios. This helps in reducing the cost incurred by the physical test. A typical computer-aided design process of a car body structure can be divided into two phases, namely concept design phase and detailed design phase. The concept design phase is characterized by frequent changes in the design of body structure. In this phase, an initial design is generated considering customer and legal requirements. Using CAE techniques, the initial design is analyzed and optimized through number of iterations until the requirements are satisfied within acceptable limits. The concept design thus created is then handed over to the detailed design phase for fine-tuning. In the detailed design phase, concepts of the vehicle body structures are further optimized and production drawings are created. Since the decisions taken in the concept design phase influence all further design stages as well, the performance of vehicle, this phase is considered to be very crucial in while designing process. The quality of the concept design generated can decrease or increase the amount of optimization required in further design stages and thereby reduce or extend the duration of design process. Although the integration of CAE techniques in the design process has made considerable improvements, these techniques have certain limitations. Firstly, the usefulness of CAE analysis results depends on accuracy of the input data used for building the numerical methods. Therefore, ability of the detain and accurate input data at the beginning of the design process is desirable for creating optimal concept design in the last possible time. Secondly, the amount of efforts and time required for building these models increases with increasing complexity of thereby prolonging the construction and analysis period. Now we'll see how to do these structures. It is necessary for car body structures to possess necessary structural performance under different types of loads and thereby provide passenger comfort and safety during the entire lifespan of the vehicle. The car body should be light in weight. However, its lightweight characteristics should not be imposed as effects on structural performance. The car body structure should provide sufficient space for the passenger or the luggage. The package components should also be appropriately supported by the body. The design of the car body structure should be cost effective considering initial investments and production aspects. By taking appropriate measures during the structural design of car body, safety and comfort of the passenger can be improved considerably. The structural design of a car body is realized considering the performance attributes like crashworthiness or passive safety, and noise, vibration, hardness, and durability or endurance strength. The crashworthiness of a car body structure accounts for the safety of vehicle, its occupants, and other participants in the event of accident. In such an event, high dynamic loads are generated at least few milliseconds. The car structure should be able to react to those in this very short duration and provide favorable conditions for the occupants. This NVH deals with the static and dynamic stiffness of the car body structure and its sound damping properties, whereas static and dynamic loads are imposed on the car body structure during its operation. Static loads are mainly of two types, bending loads and torsional loads. Bending loads are extended, for example, from the self weight of the vehicle and the weight of the passengers and luggage. The car body is subjected to torsional loads, for example, while moving on uneven load, when all tires are not in the same level. In order to sustain these loads, the car body structure should possess sufficient bending and torsional stiffness. In addition to these static loads, dynamic vibrations are induced in a car body through the engine, the drivetrain, and movements of the axle. The car body and other vehicle subsystems are needed to be designed in such a way that their natural frequencies of the vibration are not coincident with each other and are not in the range of the first natural torsional and bending frequencies of the vehicle. If the car body has natural frequency in these ranges, it may resonate and shake during the operation, generated discomfort. Therefore, the car body structure should be appropriately designed to possess high dynamic loads. The dynamic vibrations generated by engine, the drivetrain, and axial movements are transferred to the flexible outer panels of the vehicle through the mounting port. This means structure-borne sound transfer. Vibrations of these outer panels create sound that is conveyed to the passenger's comfort. Also, The sound emitted by the engine during its operation is transferred to the passenger compartment, causing discomfort to the passengers. In order to minimize the structure-borne sound transfer, the mounting parts of the engine, the drivetrain, and axle should possess appropriate damping characteristics. Everything would be taken care in the area NVH. And moving on to durability, the durability is another important attribute of the car body structure considering during its design. Passenger vehicles are subjected to different types of loads during their service life. These loads can vary from constant loads such as curb weight or residual stresses in the components to random vibrational loads imposed due to uneven road surfaces. Such loads induce dynamic stresses in the car body structure over its entire service life. Durability or endurance strength of body structure is its strength to withstand these accumulated dynamic stress over its lifespan. These three are different areas, but all areas will work for the structural design itself. Then, see, Environmental Protection Agency and that's called as EPA and National Highway Traffic Safety Authority (NHTSA) jointly developed greenhouse gas GHG emissions and CAFE (Corporate Average Fuel Economy) and to apply light-duty cars and trucks in the model years of 2012 to 2016 first phase and 2017 to 25 second phase. The final objective of these standards to achieve 163 grams of CO2, which is almost equivalent to 54.5 miles per gallon in the year by 2025. So we have a lot of methodologies to increase the fuel efficiency, like rolling friction reduction, aerodynamics improvement, drivetrain improvement. Most of the researchers proved that the weight reduction is the best methodology to achieve more fuel efficiency, and proved that 10% reduction in vehicle mass can result 6 to 7% fuel economy improvement. Because vehicle mass is a fundamental part of the vehicle CO2 emissions, and the ultimate vehicle load, that is road load, is tied directly to the vehicle weight, and reduction in weight causes to the reduction in required energy and thus reduction in CO2. See, generally the lightweight design methods can be classified into three categories as per researchers. Those are depending on perspective followed, namely strategic, constructive, and principal lightweight design. Whereas the strategic lightweight design represents various strategies such as use of lightweight materials, application of optimum geometry, etc., which can be employed for constructing lightweight constructs. The constructive lightweight design suggests various construction approaches to resolve the weight-related issues of vehicles and their components. And the principal lightweight design gives priority to the fundamental aspects of the components. A suitable lightweight approach is chosen in such a way that none of the functions of components are compromised due to the reduction in its weight. Although a basic distinction exists in these three categories, a particular lightweight design method can often be classified under more than one of the above categories. Different methods applied for lightweight design vehicles are material lightweight design, production lightweight design, shape-based lightweight design, conceptual lightweight design, and conditional lightweight design. In material lightweight design, using lighter material variants, the weight of the components can be reduced. The alternative materials to be employed is chosen considering the material cost, the production cost, and manufacturing possibilities. Additionally, care is taken that functional characteristics of the components are not adversely affected. Generally, changes in materials are accomplished by changing the geometry and the construction concepts. Conventionally, mild steel was the most popular construction material used for car body structure, right? Although lighter materials increasingly being used in the car body structures include high-strength steel HSS, advanced high-strength steel called as AHSS, aluminum alloys, magnesium alloys, and plastics. Due to considerable high strength of HSS and AHSS, the thickness of car body components can be reduced without compromising their strength. Aluminum is another lightweight material properly being used nowadays. It has significantly lower specific mass compared to conventional mild steel. The comparatively lower strength of aluminum can be compensated by thicker body components without increasing much of the weight of the car body structure. And suitable material process of aluminum for manufacturing extruded sections permit the use of aluminum for construction of lightweight face body structures. We call that as fiber reinforced plastics such as CFRP, carbon fiber reinforced plastics, and GFRP, glass fiber reinforced plastics, also offer high potentials for reducing the vehicle weight. Typical examples of components made of plastics are outer skin components and wheel rims. We have one body type that is called as a monocoque car body construction concept. There, the fiber reinforced plastics can also be used to construct complete passenger compartment. And in production lightweight design, application of special manufacturing process can be helpful in reducing the component weight. Use of manufacturing techniques such as tailored blanks, tailored tubes can be classified under production lightweight design. Using the techniques of tailored blanks, metal sheets with variable thicknesses can be produced. Consequently, areas of component requiring high strength can be selectively made of higher thickness, and oversizing of the component can be avoided. Weight of the vehicle can also be reduced by changing the joining techniques. Application of adhesive, soldering, laser welding techniques can be useful in reducing the vehicle weight. The use of lightweight materials for construction of vehicle components often alters the manufacturing process employed. For example, aluminum extruded profiles can be used instead of deep drawn steel sheets in order to reduce the weight of the components. In shape-based lightweight design, optimum distribution of material in the component is another method used to reduce the weight of vehicle, which can be classified under shape-based lightweight design. Right? The basic principle followed here is using the material where it is necessary by considering the load distribution in the component and manufacturing restrictions. Accordingly, the areas which are highly loaded are reinforced, and the regions with lower loads are designed to possess lower strength, thereby reducing the weight of the component. Integration of beads, ribs, rivets, and the sheets are example of this constructive shape-based lightweight design. Using these techniques, the thickness of the metal sheets can be reduced. Computerized optimization techniques such as topology optimization are increasingly applied for the shape-based lightweight design. According to the load distribution in the component, topology optimization technique optimizes the distribution of the material. Designing the topology of car bodies using this method is nowadays becoming more common practice in any industries and researches. And in conceptual lightweight design, the basic principle of conceptual lightweight design method is to choose an appropriate construction concept for the vehicle or its components by considering their functional requirements and production parts so as to reduce their weight. The basic concepts used in the conceptual lightweight design are differential and integral construction concepts. For these concepts, the distinction lies in the number of functions performed by a single component. According to the integral constructive concept, a component is designed to perform more than one function. Thereby, the number of components in the systems are reduced. Since no extra elements are required for assembling the components, lightweight systems can be designed and produced at a lower cost. However, repairing costs can be considerably high for the integral construction concept, as the whole component has to be replaced in case of damage. Self-supporting body structure is an example of this integral construction concept. The metal sheet components of this body structure perform both the functions of carrying the load and acting as an outer layer of the body structure. Right? And on the other hand, according to the differential construction concept, a single function is assigned to each component and thereby increasing the number of components in a system. The components can be constructed using different materials and different wall thickness, and thereby the weight of the system can be minimized. Reducing repairing cost is an advantage of this concept, whereas high assembling cost and efforts are disadvantages. Profile-based car body structure is an example of this differential construction concept, where the profiles of the car body structure carry the loads, whereas the function of covering the body is performed by the skin, which can be made lightweight materials. Different layouts of the drivetrain, such as front engine drive, front engine front engine rear drive, etc., can also be considered as conceptual lightweight design. Depending on positioning of the drivetrain component, the number of components required may increase or decrease, and thereby contribute in creating light or heavy systems. In conditional lightweight design, investigating the influence of external factors on the vehicle, such as road conditions, misuse conditions, legal safety requirements, etc., and optimizing the design concept according to minimize the vehicle weight is called under conditional lightweight design. Generally, all the vehicle components vehicle components do not have same lifespan, right? Some of the components are over dimensioned. By designing all the components to several of the same duration, lightweight components can be constructed. And different automotive market segments have different requirements for the vehicles. Difference in the performance requirements of off-road vehicles and city vehicles is such an example. By considering appropriate requirements, city vehicles can be designed to possess lower strength and consequently lower weight compared to the off-road vehicles. Right? Similarly, considering only these misuse conditions applicable for a particular vehicle can help in designing lighter systems. However, it is not always possible to use conditional lightweight design, as it is generally difficult. Difficult to decline the exact conditions that may arise during the operation of the vehicle. So, lightweight design of the vehicles and the car body structures provides advantages in many ways. It also has some limitations. Reducing the weight of car body may have adverse effects on the strength, stiffness, and safety performance characteristics of the body structure. Using alternative materials for lightweight design increases the costs of manufacturing if these increased costs are not compensated by the reduction in fuel consumption or by increased vehicle performance. The overall cost of the vehicle may considerably increase. In order to make optimum and efficient use of alternative materials, suitable and cost-effective manufacturing and joining techniques should be available. Recycling of the car body structures constructed using a mix of materials may show undesirable effects in the environment. In order to use the lightweight design methods effectively without any adverse effects on the performance of the vehicle and on the environment, conducting a thorough risk analysis is always recommended. Assuming the performance and customer requirements can help in identifying weight reduction potentials and in choosing suitable design strategies for the body structures and other vehicle systems. A crashworthy car body structure is so conceptualized and to observe considerable amounts of the impact energy by deforming in definite areas and thereby reduce the deceleration experienced by its passengers to survivable levels. The non-deforming areas of the car body structure are designed as stiff survivable space for the passengers. Various criteria such as deformation pattern, deceleration paths of the vehicle, different biomedical criteria defined for passengers, etc. can be used for assessing the crashworthiness of the vehicles. Before going into the crashworthiness in more detail, we'll just see a small video where our Maruti Suzuki Baleno car has been conducted for crash test by the Euro NCAP, means European New Car Assessment Program. This is the test of frontal offset impact barrier. Here the deformable barrier is used. Just remember that deformable offset barrier. I'll let you know what it is exactly in future slides. These are the child dummies placed inside, and male and female dummies also would be placed inside that. This is the physical real test conducted by NCAP, and this is full frontal rigid barrier test. This would be conducted at 50 kmph as per norms. And for this test, our Baleno got 3-star rating. See, this video is in slow motion. It's not exact speed. This is side impact. Whereas this barrier would be in movable barrier, vehicle would be in static position, and the barrier would be in movable, where the barrier speed would be 50 kmph. This would be called as side pole test, whereas vehicle would be moved and the pole would be in standard position, where the vehicle would be moved with 32 kmph velocity. This is called as whiplash test for occupant and neck injuries and all the things. This would be for pedestrian safety, head impact test, and this is for leg impact test for pedestrian safety. This is also leg impact pedestrian safety. And whereas this vehicle with auto safety ride back braking system would be tested. So this is the physical test conducted for our Maruti Baleno model 2008. Just imagine that for every test we need to spend one new car, which costs most amount, right? For that, people will go first for CAE analysis. Once it's get passed, then they will apply for physical test and they will get certified and they'll get that star rating. See, now we'll move into principles of crashworthiness. Why I shot that video is once you see that physical video, you can come to know what is crash. You'll have some glance about that. Then you can catch whatever the statements I say, right? And yeah, the the foundations of crashworthy design for a vehicle were laid by the engineer Bela Barney during 1940s at the Daimler-Benz company in Germany, which is independent of the developments in USA. He developed various concepts for achieving passenger safety. So one of the main concepts being that of the crumple zone. This basic principle is still followed today for designing a crashworthy vehicle structure. See, here a stiff passenger compartment is constructed and it is surrounded by predefined energy absorbing zones called crumple zones or deformation zones. These zones are situated at the front, rear, and both sides and top region of the passenger compartments. A deformation zone can be divided into primary and secondary deformation zones. The primary zone consists the main energy absorbing structures, whereas the secondary zone is a structural interface between primary zone and the stiff passenger compartment. The secondary zone acts as a stable platform for progressively for the deforming primary zone and transmits the load to passenger compartment. The secondary zone can also be designed to deform in controlled manner in order to reduce the energy flowing into the passenger compartment. However, the load levels situated by the secondary zone are kept higher than those sustained by the primary zone, thereby ensuring that the components in the primary zone deform before the components in the secondary zone. The passenger compartment surrounds the deformation zones and provides survivable space for the passengers. The deformation zones, together with the passenger safety systems such as seat belts and airbags, helps in reducing the deceleration experienced by the passengers. Various methods have been developed and used over the years to analyze and optimize the crashworthiness of vehicles. We will see some of the most popular methods and their advantages and disadvantages. The most popular method in use today for analyzing crashworthiness of vehicles is computer-aided nonlinear finite element method. According to this method, a continuum is divided into finite number of subsystems called finite elements. The state of the whole continuum can thus be described using a finite number of parameters such as displacement, forces, etc. and each node of Fe resulting in a set of equations of motion. These equations are solved using numerical techniques and thereby an appropriate behavior of the continuum under the given loading conditions is studied. Owing to the continuous improvements in computer hardware and software as well as in the numerical structure mechanics, the Fe method has become more efficient and accurate since its introduction. Whereas softwares such as Radius by Altair Engineering, LS-Dyna established by LSTC, that is Limo Software Technology Corporation. Now it is hired by ANSYS, and PAMCrash by ESI Group, etc. are used in today's automotive industry to analyze the highly nonlinear and dynamic problem of the vehicle crashworthiness. Depending on the phase of the design, the complexity and size of Fe model varies considerably. However, the Fe models are or FE method has some limitations. It gives an appropriate solution of the problem and however may not always represent the reality. Certain amount of expertise is needed for using this method effectively. Due to advances in computer technologies, the speed and what you can call accuracy of regenerating FE models and simulating them has increased. In spite of these advantages, modeling of complex structures, building a numerically stable model, and getting realistic results is still in time-consuming task for these analysts. Moreover, due to the detailed input data needed for building an FE model, such as material and geometry data, these models prove to be less useful in concept design stage of a vehicle. In this stage, the design concept changes quite often and different design concepts are evaluated against each other for their crashworthiness. Therefore, considering the efforts needed to building a single FE model, this method is not always suitable for the concept design phase. Another analysis method was primarily used for analyzing vehicle crashworthiness before the advance of FE method is the lumped mass spring method, also known as LMS. These LMS models are simple models that approximate a vehicle as one-dimensional model consisting of a system of springs and lumped masses. The springs mainly represent the deformable structures of the vehicle, whereas the lumped mass represents non-deformable components of the vehicle. The load deflection characteristics of the springs are determined either from test of the respective deformable structures or from their validated FE models. The LMS models prove to be very useful in designing vehicle derivatives or upgrading the body structure, where the crash performance results in the basic model are available either in the form of tests or FE simulations. However, for designing a completely new vehicle structure, the LMS models are not beneficial since in this case the spring characteristics are unknown. The accuracy and reliability of the LMS models heavily depends on experience, knowledge, and understanding of vehicle crashworthiness of the design engineer. The simplicity of LMS models and the flexibility of FE models is combined into so-called hybrid models by researchers in an attempt to overcome the limitations of both the methods. The most common approach followed by various researchers is developing a collapsible beam finite element and integrating into FE software. Different concepts and formulations are developed and used by different researchers, such as elastic plastic beam, super collapsible beam element, super folding elements, and super beam elements, etc. The formulations of these elements follow various simplified approaches ranging from purely analytical to purely experimental. In order to construct a safe vehicle, it is advisable to consider certain crash scenarios such as frontal crash, side crash, rear crash, and roof crash during the design vehicle. This slide gives somewhat details of legal crash scenarios and consumer protection regulations relevant for the passenger vehicle. So you can see different impacts over here. Yeah. If we consider frontal impact, it has some different scenarios like FMVSS 203, 204, 205, 208, 209, 10, 12, 301, ECA, R12, different regulations only for frontal impact. And for bumper impact, we have FMVSS 581 EC R42. Whereas we are using EC R14, EC R12, EC R42. And for pedestrian protection, we have some legal regulations, European country regulations 78 2009 and ECR 127. And for rear impact, we have FMVSS 202, 207, 233, 301, ECR 17, R25. And for seats also we have some FMVSS, and for side impact also we have some regulations. Different legal regulations were incorporated in Europe and EC. Even for India also we are following some legal regulations whatever are available in Europe. Even we just seen that for a Baleno crash test. We conducted that in India, but we followed European regulations. Based on country regulations, we can adopt all these legal regulations. See, whenever we say legal regulation, that has certain structural procedure. We need to strictly follow that. I can say one example. If we conduct some ASTM test, we need to follow a specimen based on that ASTM standards. Like that, to conduct any crash test, we need to strictly follow these legal regulations. And after obtaining these legal regulations, well, in our Indian government also announced these legal regulations. Somewhat missing it. And they incorporated some legal regulations and standards for that. Based on that, every vehicle has to go crash test whatever is being manufactured from 2019 onwards. Whatever the vehicle, if you would like to make production, we need to go for crash test physically from 2019 onwards. And whatever the vehicles already produced, those has to go for crash test from 2017. I think you might be observed from 2019 onwards, we are observing most of passenger vehicles come with a new concept called as facelift. I think most of the people observed that. Facelift, that is to incorporate or to add more strength for frontal impact, right? And at the end of this crash test, they will announce star rating of that particular vehicle in terms of single star, double star, 3 star, up to 5 stars. If our vehicle gets single star, that means marginal crash protection. People may die also, not people exactly, that occupants. And if the vehicle gets 2-star safety rating, that is nominal crash protection but lacking crash avoidance technology. If the vehicle gets 3-star safety, that means average to good occupant protection but lacking crash avoidance technology. If the vehicle gets 4-star safety, overall good performance in crash protection, additional crash avoidance technology may also be present. If the vehicle gets 5-star, that is top star rating, overall good performance in crash protection, well equipped with robust crash avoidance technology, right? Are there some legal regulations to be incorporated for CAE analysis? This is one of the sample regulation. Options, laser pointer. Yeah. See, in earlier we just gone through frontal offset impact, right? That's called as ECR94. Frontal offset means the front portion of the vehicle should be offsetted with 40% touch with vehicle of this barrier. If it is a deformable barrier, that barrier should be deformed. As per the naming convention, if it is deformable barrier, this ODB means offset deformable barrier. It is an offset with 40% touch with the vehicle and 60% in open. Right. This is the top view, and this is the full frontal impact, called as FMVSS 208. In this, the barrier would be rigid wall, and 100% of the vehicle should be in contact with that barrier. And this is the side crash test with the moving deformable barrier. This side barrier would be designed with the IIHS, and this is ECR95, whatever we are using. This barrier will hit exactly B pillar of our vehicle, whereas this has a full offset and oblique offset are different methodologies. This is the side view of that side deformable barrier test. This one is the barrier. It hits exactly the B pillar. You know the pillar, right? This would be called as A pillar, and the pillar is whatever is there in between front door to back door would be called as B pillar, and the pillar back to the B pillar would be called as C. If it is SUV vehicle, we will have D pillar also, right? This barrier would be positioned to hit B pillar. And this is rear impact barrier, called as ECR34. Here 70% of the vehicle should be in contact with this movable deformable barrier. A deformable barrier will hit the vehicle with 70% contact. This is the top view, and this is the side view of that scenario. This would be held with 40 mm. And these are the different scenarios what we need to follow. For frontal impact, if we consider FMVSS 208, that type has rigid barrier, and the overlap should be 100% overlap, and the velocity of that traveling vehicle should be from 32 to 56 kmph based on micro size passenger vehicle and mid passenger vehicle. As our this Baleno is mid-size passenger vehicle, that has to be conducted at 56 kmph. Micros compact cars means like nanos and all the things, micro cars. And in this frontal impact FMVSS 208, we have 0 degrees and 30 degrees. Means this frontal impact would be in 0 degrees, means full frontal with full contact, and 30 degrees oblique. And ECR94, in this we need to use a deformable barrier, and the overlap should be 40%. 40% of contact of the vehicle should contact the deformable barrier, and that barrier size dimension should be 1000 by 450 by 650, and this should happen with 56 kmph. And for pole front impact, that pole should be rigid and dimension should be 250 mm, and the velocity of vehicle should be 30 kmph with 0 degrees oblique. That one should be in any angle. Whereas our Euro NCAP pole crash, same thing, but the velocity would be in 29 kmph and 90 degrees barrier, means side impact pole crash. This side impact deformable barrier, called as ECR94, it has barrier dimensions 1500 by 450, and the velocity should be 50 kmph, and the angle should be 90 degrees, as it is side impact. The rear impact, called as ECR34, the barrier should be rigid and overlap should be 100. This is the dimension, and velocity should be 35 to 38. These are the primary regulations, whatever Indian regulations will conduct. And if we see the physics behind this is, just assume that if two vehicles are in collision, vehicle 1 and vehicle 2, as per the energy equations, we know law of conservation of energy, right? Based on that, the total initial kinetic energy should be equal to the summation of translational kinetic energy after impact and rotational kinetic energy after impact and energy of deformation, right? We know that energy can be neither be created nor destroyed. So the total kinetic energy before should be the summation of this. This is the physics behind any crash scenarios. Just assume that if one of the vehicle is not a vehicle, it's a barrier, then this conservation of energy will be converted into like this. This one, we can imagine that as barrier. It won't have any initial kinetic energy. We'll have only one kinetic energy of the vehicle moving. This total kinetic energy of the vehicle would be the summation of that energies, right? If we have two vehicles, that conservation of energy will be like this, and if we have only one vehicle, the crash scenario energy conservation will be like that. And we just did one case study at NIT Warangal to achieve crashworthiness, which is almost equivalent to 5-star energy crashworthiness of BMW high-end. We just did a benchmark analysis for 5-star vehicles, and we consider those as target energies, and we consider a micro passenger vehicle. We developed a CAD model and a CAE model of BIW for this vehicle, and we conducted various FE analysis by using HyperWorks and LS-Dyna, and we achieved more crash rating than 5-star, what is available in a BMW 5-star. In this, I don't want to show my BMW work, what I did. This is the sample styling case, which I got from one of the automotive industries incorporated in USA. This is a FE model of a vehicle, micro, 2-passenger vehicle. Just imagine that it got 5-star rating, which is almost equivalent to the BMW high-end car. We have very less crumple zone. It seems like nano car, which has which seems like a facelift, right? And we followed 3-level crash test for that. We assumed that level 0 is nominal, minimum, and level 1 is mid-range, and level 2 is high-end range. And we classified all the things based on this. So you can imagine that, or you can observe that, if you need to pass legal regulation that has to pass level 0 test, those are EC R94 and EC R12, and also pedestrian safety also. You can imagine that nowadays pedestrian safety is become more crucial. Even central government made regulation to avoid metal bumpers also for the vehicle. Why? Because if we add metal bumpers over here, the safety for pedestrian will lose. The basic concept for this bumper is for pedestrian safety. Just observe that our older vehicles like Jeep and all the things will have metal bumpers, right? Whereas our new vehicle is having plastic bumper panel. Inside that bumper panel will have foam and structures, all the things. Why? Because whenever pedestrian hits or our vehicle hits that pedestrian should not injure more. And consider that pedestrian hitting speed is maximum of 40 km/h. That should not be more than that, right? And in level 1, if we would like to pass level 1, we should pass level 0 first, and then we need to pass level 1. If our vehicle needs to pass level 2, that has to mandatorily pass level 0 and level 1 scenarios. Then we need to achieve level 2. This is the scenario and a sequence per legal regulations. This is our vehicle. These are our the targets, what we targeted for our microcar. We just took 3 stages to observe all the energy. First stage is up to 200 kilonewtons, whereas this crumpled displacement should be less than 100 mm. And in second stage, 200 to approximately 400, and the crumple zone should be max of 300 mm. Whereas in third stage, it has to observe 500 kilonewtons, and that overall crumple zone should be max of 350. Just imagine, in 350 mm, we targeted to achieve 550 kilonewtons, and we achieved that. Yeah, that's all my presentation. If you have any queries,